Okay, we are back. What I last was working on was the Python sample code that basically takes in our data set, splits it up into our train data and our test data, create a subset of the train data, and basically run a classification type of analysis. In the middle here, we have plotting of the distribution of the attributes of the data set. And then we go into basically calculating the coefficients and calculating the prediction value. And we were able to demonstrate that you can see difference in prediction values between using obviously a differing data set or version of what I'm using here. So one thing that I thought about that I need to do is I will go ahead and produce the other part of the data set, the subset. So maybe I'll create a subset A and B data. So what I need to do is create the subset for each of these, because I should test that, once the datas are calculated, I should be able to combine the separately calculated datas, and then I can use that to run the test data, and I should get the same prediction value as I get for running it with the full data set. I just thought of that because when it comes time to turning or applying this to the Nada program, what I'm trying to avoid is the use of the Python libraries, because I believe we're just needing to use these built-in operations. So let's just try to do that. Start from the top. So here's the train data set. So here's the 25%. What I really need to do is handpick this 25% so they can give me a skewed result or something. That way it's just more visible in the prediction difference. Again, in the real world, there's probably different ways to do this. I'm just showing how beneficial this potential blind computation with Nillion can do when it comes to performing like analysis and whatnot, when you have different healthcare networks with different sets of data. And the goal is we can combine these available data without each health provider having to reveal the specifics of their data set, because I think data is power, and it's hard for me to see how one healthcare provider will lose out in their leverage in their data set by providing the raw data to another health provider. Still a competition when it comes down to the different health provider networks. So let's go ahead and create a different subset. So this is 25%. What I should do is call this subset large and small. So maybe this will be let's just find it. Oops. Data. Yeah, on that. All this small. Okay. I just 20 size, 25. All right, so we got 25% of the trained data. Yeah, so create a subset that is 75, which will be subset 25 will be 75. And then we're going to use the same as that test data. So we will do train data and then the subset colon. All right, that should work. So we should have it plot all three distributions of the data sets, full, 25, and the remaining 75. And then X test augmented should be fine. It's just really the one test. In the in the I think a real evaluation, you'll run all the test samples and you would have some evaluation measurements. But yeah, this is not performing a full classification. We're just wanting to demonstrate that Nillion can do the blind computation, or an approach, I guess, to using Nillion to perform the blind computation part. So we have the X augmented. So this needs to get updated. I think this works for now, and then we need to combine the coefficients and then run the prediction through the combine. The combine part. So let's just see what happens here. So let's see the first. Should think about fixing that. 1, 2, 3, 4, 5, 6, 7. If I do 6 rows, we would get one more. Nah, we'll just keep it. Okay. So this is the full data set. Total, I believe there's like 80% of over 500 instances. If you combine the distribution, it should be around, just 250. And there should be the 80%. And then when we close this, we should get the smaller subset. So this is definitely looking smaller here. And then if I close this, we should get right here the 75%, the remaining. Okay, so from that, it'll continue to run. Let's just see what we got. I'm not sure what our test data. So I'm not sure if I'm using the fixed one, maybe. So it's the test data is a sample with a diagnosis of 0. So I should expect a lower value. And we can see that the normal data set is at 0.13. The smaller is at 0.10. And then obviously the larger of the subset is closer to the full prediction value. So looks good. What I want to do now is combine the coefficients between the two subset and then run the tests through through that value, then that way we should be able to show that the combined coefficients should equal as if it was, ran as a single database. Then the goal is to perform, the computations and calculate the coefficients in each of its own data sets. And those coefficients will be used as the secret inputs for the party. Each party will be each healthcare provider network. That way, then you can perform the what I'm hoping is we can perform the combining operation with the auto program, and then we will get the resulting coefficients. And then from there, you're able to run test data on these, combined coefficients to get the results of a predicted value. And by doing that, you can say that, both subsets of data from each healthcare provider, that none of the actual data set was shared during the computation. Okay, let's go ahead and do the data combination calculation part. Maybe I'll put it right before that final computation. Don't really need it. So compute prediction using combine, calculate the weights for each subset. And this is, I should not do this here because it will not make it proportionate. So and then basically just use the weighted averaging. So let's do the combine data, and all we need to do so do the theta, no, theta of the subset small multiply. Let me do the same for the large. Make it on this side. And then I think we should have data subset small, data subset large. So there we can see that the value is much closer than how I had it weighted earlier. This should be good. So what's next? I'm Chris, and I'm still working on that hackathon project for ETH Global Scaling Ethereum. And this project is using the Nillion protocol. What I was last working on was the sample Python file that contained the logic of what I'm hoping to demonstrate, where we would be able to show some blind computation across two data sets. And I ended up refactoring a little bit and just turning that Python file into just a program. So here in this healthcare imaging compute folder, we basically now have this app program, and it's just small refactoring, real small refactoring, but I think it will help when I want to start creating the Nada part of the program. We'll see. It should still work the same. So here's the functions for the plot distribution here. And then we'll go over what this scaling factor that I added to the program. So let's just give it a run. Python 3m module. So we should see 3 figures. The first one is the full data set. The next one is the smaller. This is the 20% of the training data set. And then the next one is just the remaining. So these are the distribution plots. And if we take a look at the data now, there, much better. You see the first 50 rows printed. Again, the purpose with that is just to make sure the code that I have to replace the M's with malignants with 1 and the benigns with 0. So we got that. And then you can see the randomly selected tests exam or text image. And then we have the coefficients. We have the coefficients for the test. And then we have the predictions. So pretty straightforward. When I started working on the Nada program, so I think it's now better to bring that into focus. So in the programs here, we can see where I left off with this program. What I realized is that the Nillion data types is taking in integers, and I don't see any floats. So figured then we just need to create a scaling factor, and that's where this function was created. So I'll uncomment the print for that so we can see the result of the scaling factor. But how it essentially goes is we want to pass in the data set, and then the precision here allows me to set how many decimal places that I want to, try and preserve in the scaling. And then we just basically use math ceiling and logs to determine this. And what I'm returning is a tuple of basically the scaled data. So I'm taking the, whatever I'm feeding into this, and then I'm providing the scaled data of it, and then I'm providing the scaling factor, which will be used then to convert it back to the descaled value. So that's what we'll see here. And I'm basically taking in the values that I plan to use in the Nada program. So in this case here, to see the start of the program, we will be creating a secret integer input for each of the coefficients. And these coefficients basically then represent, the test model for each of these data sets. Each of these coefficients will be for the corresponding data sets that it belongs to. And working through this, I'm thinking of doing 3 parties. We'll have a party for the patient, and then we'll have the health provider 0, if that makes. And then we'll have a party called health provider 0. This I plan to use as the full data set. And then we have 1 and 2 for the other split data set. One will be the larger and another will be the smaller. And where I was following to guide myself in creating this program was using that coefficient file. So I have it in the original Nillion, the Nillion starter. So as we see here, I'm just using their program as a guide in how to create, the program for mines. So we can see that's where I left off, and I'll continue. But to take a look at this scaled coefficient factoring that I did add, let's run that so that we can take a look. I'm just going to close these three figures. And then let's take a look at. Okay, so again, the first data table that we see is the first 50 rows. Then we get this test data. Here we see the scaled coefficients. And as you can see now, I basically shifted so that we don't see the decimal places. And then for each one, we can see what the scaling factor was calculated as. And that is the equivalence of, the original unscaled coefficients. And what I did was basically ran the same type of computation to do the predictions. And then let's see if nope, so I actually forgot to, so I might have to run this again. So I forgot to uncomment the scaled test data part so we can see. And obviously due to potential rounding, the values may differ ever so slightly. And I'm just going to comment out the plot distribution so I don't have to waste time closing out the files. So let's take a look at the data again that I just ran. So the first is the 50 rows, the second is the test data. And now here we see the scaled coefficients and the scaled factor. And essentially we just shifted the decimal to capture the values as an integer. And then we still perform the same prediction calculation. So the first part here, we're calculating the prediction just without the scaled factors. And then you can see here, we then have the predictions using the scaled numbers and then actually descaling it. So you can see here's the prediction for the full test data, 436433. And here's the prediction for the test data. Or this is the scaled. Sorry. But very close. So that's as expected. And again, the reason for needing to scale these values is because in the Nillion data types, just making sure we can handle numbers or numbers that are. So let's continuing on this here. In the program, I need to set up the secret inputs, and here I've put it a fixed expected number of coefficients that we expect the program to take in. And we're basically we're labeling these inputs. That's the point of this for loop. And as we see in when they were creating their vectors here. Okay, I see. They're just creating their labels of the party on top. I think what I can still do is just use the patient to have access to the outputs. I don't think in this correlation coefficient, it's just defining an out party. So we'll run into that if I need to update that. What I did notice was, because in here they created their arrays of parties. Going into the program here, we now can see the scaled datas, and that's what will get fed into or stored into the NADA program. Well, here's the example working with the arrays and tuples. So they have created 4 secret integer input, A, B, C, D, and all belong to party 1. Then they set up a tuple, which takes in A and B, and then they have another tuple that takes in C and D, and then they create a new array which takes in both the tuples. At the very end, the output, we're just getting a predictive result. So I don't think it even matters about the tuple anymore, because I think I'm just overthinking it. And what's going to happen is we're passing in the coefficients into the NADA program. So we pass in the secrets, then we can store the secrets, and we bind it to the program. And then when it's bind to the program, that's where then we're able to perform the computes. Like, for example, here, if we just look at the multiplication, we are creating the secrets, and then we bind it to the program. We store the secrets. We have the cluster ID, the bindings, the stored secret, and then we can run the compute. We can use computation time secrets, or maybe for the patient. Yeah, I like that. So if I look at the NADA program for the multiplication program, so I can see that this will be the compute time. Party 1 has access. This is what's going to be stored. So in my case, I can have all these health providers store the data set. You can store the data set. Technically, this does not matter. I think we need to just remove the case of health provide 0, because that is something we just compute outside of the program, because if there's no point adding all that. So the compute time will be this party patient. So then that's will be patient test. No, what am I doing? There's only one value that's going to be returned, and it's going to be the out prediction. I think I just need to finish the NADA program. I was able to rule out that deleting some of these programs and whatnot still allowed me to run that compile program, which is going to be needed. So let's just go ahead and work this one out. So the idea is we will pass in the two parties, which is going to be, we have two parties, separate data sets, and coefficients will be the same. It's the assumed where, they're doing it. The assumption is the diagnostic type of test is imaging cancer test. And so you'll probably want to keep the same coefficients. And then we'll have a party for the patient. So let's get started. So we have set up the secret inputs for the coefficients, because that's what we will be passing in. And I'm continuing with the Nillion project for the ETH Global Scaling Ethereum hackathon. And I've done a lot of changes since the last time I started recording. One of them was I moved the program structure back to how the sample programs were created in this Nillion Python starter. And I just trying to figure out some errors that I had when it comes to getting the Nada program integrated. The Nada program itself is compiled and everything seems to be fine in the files that were created in the program's compiled folder. What I just need to figure out right now is to get the Nillion section in my Python file working here. So I updated the Python file to classification model. You know what? Just thinking about it again, maybe I should just keep it the same. I don't know. Healthcare, imaging, compute. Yeah, we'll just keep it the same. So I also updated the Python file a little where I can pass in a flag to disable the plot. Let's run that, and I can pass in the disable plot. Yeah. Okay, so that worked. And I have a bunch of errors. That's for the Nada section, but I've formatted some things too in the printouts. I'm not sure where I'll get to. Today is the last day for the hackathon to work on it. Well, technically, I have till 9 a.m. tomorrow here in Pacific time. And my goal is to get this part of the Nillion part in the Python file working. That way, then I can start looking into possibly bringing in the ETH scaffold into play with this project. But given the time as well and how soon I'll look into this, I'm also wanting to start working on the README. README is important in the hackathon, and even to begin figuring out what type of demonstration video that I want to record, and kind of send that message of my purpose behind this project. But that's the intent and that's the goal. It's just to keep moving. The issue I have here is it's not reading the user keys. So let me look at how the sample program works. So there's a multi-party compute. A lot of things I don't need right now. So I'm looking at the original Python starter repo on this little screen, and I deleted a bunch of the starter repos files because just to focus more on what I'm trying to build, and I just referred to this repo to look into the examples that they use. But let's see what's going on in there. In this one here, the multi-party compute program. And I just want to match it up with, what I'm trying to build. Okay, let's just move on to the health provider part. I think this will bring it in more, make better sense. So what then? So the next part in our program, we just want to start moving on to setting up the other clients, which is going to be the health provider 1 and 2. Oh, why don't I just do that? I can see in my head, I'm seeing we can use the config file just to modify the split in the data test split. Instead of going into the code, why don't I do that? I implement their 4-party info loop for each health provider party in config health provider. It's probably not the name. Yeah, that's the name. And then we do that client n equals create client. Yeah, looks good. Create Nillion client, and then same thing as what we did for party 1. We will use the get user, get node key, and in the for loop, it will do lookup for the user key files. So in here, just to make sure user key files, yep. And then in the config, we're just assigning it to these party 1 and party 2 that the Bootstrap local environment program, basically, I think it's this that's set up, because in the environment variable, we can see that it provided us these node keys and user keys when you run that Bootstrap. So what then? What's next? We go into storing, which in our program, we're going to set up the dictionaries. Or we can get the party ID. Let's do this first. So we do the party IDN. It's client party ID. The user ID. Yep, looks good. And then we do, yeah, pretty much. Yeah, I think I'm just wasting some time. I think, again, the point of the demo is to run the calculations outside of the Nillion program, and then running the calculations in a way where you can, produce it or compute blindly and compare some values. So I'm just going to do it this way instead. Set up the party IDs and users IDs. The ID for provider 1. User ID. Let's go to, okay. And then we have the program path, which just go up here. So the client is patient storing the program. And now we have the action ID and the program ID. Now let's set up so let's create secrets. Health provider party. So we have health provider 1 and 2. And then let's go ahead and add this guy in. I'll get into this one later. No, we can do it now. Okay, so let's just, we're creating the secrets for parties, for all parties. Patient test party will be time. And then health writer 1 and 2 will be stored secrets. Okay, so we basically take values and you're needing to turn it into a Nillion secret. So we have that. Now we can you know, print these guys. I think it should work. And as we see in the Python startup, they're doing the binding part. So the binding and the permissions part. So that's what I have here. So let's go ahead and grab this. Let's copy it over. And what we can do okay, let me kind of retract. So creating the secret for the current parties, and what it's done here is we have the secrets. So Nillion secret integer for this patient party. Okay, we have that. And here's the stored secrets. Nillion secrets, and then we have the secret integer inputs for each of the health provider health providers. That's we have 1 and 2. And then we can do the bindings part. Okay, so secret binding, Nillion program. And then we do the secret bindings add input party, and there's the party name and the party ID. So party name, config health provider parties 0, and we want the party name. And then this will be the second party. Okay, and then we need to bring over the party IDs. Party ID. Okay, and the next one is to give permissions. So we give permissions for the health provider 1, health provider 2. Like this description here, give compute permissions to patient party, patient test party. Okay, let's stop it right here. So what then? Well, I did it. I got to submit it like 5 minutes before the deadline. It wasn't what I was hoping for. I was hoping to get it completed probably yesterday at some point with the whole submission completed. But I was having a lot of issues still trying to get the Nada program going. And eventually I figured it out what my issues were. I think part of my issue was where I'm activating my Python, where I'm activating the Python environment, because that affects some of the starter repos. I believe that where it's looking at the environment path or something like that. But once I got that figured out, I mean, here's my finished of the program. Once I figured that out, though, if we go to the Nada program, what I ended up doing, which I should have done it before, was I created a bunch of these outputs. So as you can see, it's an array or a list of returns. And how it basically works is you can, just basically create as much outputs as you need, as long as you have the label. And then on the client side, you'll be able to refer to the label. Or actually, if we go to this guy here, at the very end, where you can pretty much, when you get the compute event result, you can pull up or do a lookup on the output. And if you don't include a lookup, it would just display everything that there is in that program. So there was a point where I was logging almost like 10, 15 different items, but that allowed me to figure out what was going on, because the issue I was still seeing, it was resulting, the prediction value was resulting to a 0 value. And I was thinking that there was something wrong with potentially how my loops were going, or how I was bringing in public or private data, secret integer values. And what I found was these were actually okay. The formulas, the loops. What the issue was, so in the weight calculation, there would be a 0 value, and basically that would cause a 0, and it would go through the rest of the program. And that's why I was pretty much seeing a 0 output. And the reason it was going to 0 is, if you're doing weights, then it's pretty much somewhere between 0 and 1. So the fix for that was scaling the weight. So when it's sent over, it was, if out in my case, I was doing 75-25. So, but what I would need to do is back out, is pretty much back out the that base multiplier. So that's why you see the integer 100 here. And then once I got to do that, I started seeing values, non-zeros. So I was happy with that. And pretty much that was what got me going. And from there, I think it was 4 to 5, I would think, basically got things working. And then it took me probably another hour or hour and a half to just start trying to pretty up the code as much as I can, and also started working on the README. And if we go to the README, just starting to do research that I should have done sooner or had. Just information just to try to create a good README. But from there, then the next step, and I think this was getting around to like 8 o'clock, I think, is when I started recording myself for the demo video. And I think then it was like 20-30 minutes probably, that editing somewhere. I think I was around, it was probably 8:45, I would say 15 minutes, 20 minutes before I started uploading. And it does take a while to start uploading the video. There was a message on there too, to not click away or anything while it's uploading, which I was hoping to move on to the different questions to start answering, but I didn't want to, cause any interruptions in the upload. So I waited till that pretty much gave me like, 5-10 minutes to just try and go through as much of the questions that I could before the deadline. And, I wish I went through that maybe sooner. But again, I spent most of the past day just trying to figure out what that issue was that I was dealing with in the Nada program. So, but the good thing is, I got this done, and it's pretty, it's surprising that the last time I did the ETH Global solo hackathon in Tokyo, it was actually around the same time where I got things going, really late in the hour. And it was, I misread the deadline for this hackathon. I actually thought that there would have been like half a week more, but I keep forgetting that when you see the dates posted, the start and end dates from ETH Global, they actually include the finales. So keep that in mind. The date that you do want to look for is the submission deadline, and that could throw you off in the planning that you're trying to do. So, but everything's finished, and I'll try and get this these videos put together.